In order to prove by mathematical induction, we have to give it a name. So this kind of proposition, we let it be Pn, and it's effective for all positive integer n. That's our target. So basically, we start from the first case. That's why we consider a specific case. Why we choose 1 is because 1 is the first case fulfill the requirement positive integer n. So that's why we start from 1. And then afterward, left hand side, we just copy down the same thing, but however, whenever we find n, we replace it by 1. This means that we are going to add several terms together from the case k equal to 1 up to case equal to 1. So basically, there are only one term. It's the single case that when k equal to 1. Then we finish the loop. We get -1 here. We are going to consider right hand side, see whether they are the same. So right hand side, we have -1 power of 1. We have 1 and then times 1 plus 1 over 2. So it's give -1 times 2 divided by 2. It's also give -1. Based on the fact that LHS equal to RHS. Therefore, we can draw the conclusion P1 is true. We already secure the starting point. If we have the starting point, then we just want to push the next one. Therefore, we assume that the general situation, Pk is true for some proof value, some positive integer k. Beware the wording here must be some only. We didn't prove all yet. It's because sometimes if we prove 1, then we want to see that the next one, whether P2 is true. After we know that P2 is true, for some positive k, how about the next one? Is 3 is correct. So we have this assumption. And then the most important thing is we must try our best to use this assumption. Anyway, you have to write down what is that implication. That means this is correct, but however, we use k as a general item in the loop. So therefore, we better use another integer. Maybe we use r. Which means that we assume when k is equal to 1 up to the case that k is equal to r. -1 power of k and then k power of 2 all add together will give you -1 power of r. R times r plus 1 divided by 2. Beware that this variable is r but not n, because n representing all positive integers. However, we are just talking about a specific case that we already proved before. And you must clearly write down your assumption so that you can use it for the following step to prove the next situation. Therefore, we are now going to consider the next case. Assume that PR is true, and then we are going to consider the next case, PR plus 1. So left hand side, you will have the summation from k equal to 1 up to k equal to r plus 1. And which means that from k to r, and then we have extra term, which is the r plus 1 case. If we break it down, that means the first term, -1 power of 1, 1 power of 2, and then plus the second term, -1 power of 2, 2 power of 2, plus the third one, -1 power of 3, 3 power of 2. Up to the situation when k equal to r, -1 power of r, r power of 2, and then this time is up to r plus 1. So therefore, this is -1 power of r plus 1. And then r plus 1 power of 2. The first r term here basically is your assumption part. So you are going to replace this r term by using this result, your assumption. So that's why it's -1 power of r times r plus 1 over 2, and then plus this one. At this moment, if you don't know how to handle it, maybe we extract the common factor 1 over 2. If we extract 1 over 2, which means every term times 2. Afterward, we are trying to simplify it, and then the best way to simplify it is taking out the common factor. I find that negative 1 part of r is common, so I try to take it out. At the same time, I think that r plus 1 is common, so I try to take out r plus 1 also. And then we are going to check each term which one is left. This one is removed, and then r plus 1 is removed, only r is left from the first term. From the second term, positive 2 here, and then negative 1 part of r is removed, so only power of 1 is left. And also r plus 1 part of 1 is left. So then we just continue our calculation and see what will happen. Is r minus 2r and then minus 2. So we get this one is negative r minus 2 here. Compared with our right hand side, we prefer positive r in the bracket. So therefore, we are going to extract negative 1 also. It's become r power 1 now for negative 1. And then we have r plus 2 is left. So now we are going to consider right hand side. Is equal to negative 1 power of r plus 1. R plus 1 times r plus 1, and then on top of it plus 1. So basically try to write exactly the same format to show that it's exactly the same. Therefore we can draw conclusion, since LHS equal to RHS, then the next case is also correct. PR plus 1 also true. Therefore we can draw the final conclusion. By the first principle of MI, Pn is true for all positive integers n, because we are going to say that it's general positive integers, so we use back n here. And then afterward, in part B, we are going to use this result is reliable now, and then we are going to evaluate this one. The key point is find out what is differences and also what is n representing in this situation. In order to use the result, it's very important for us to label what is the differences between our target and also the tools that we can use. First, it's obvious that n representing 3, 3, 3. We are going to use it. But at the same time, beware that this is k plus 1, part of k plus 1, while this one is k only. So we are going to isolate this item. We just extract negative 1 outside, and then this one will become negative 1 part of k only. Afterward, there's still some small differences about the starting point here is 3. However, our target is from 1 here. So in order to do so, we prepare a bracket here, and then we are going to add back 2 cases so that it starts from 1. We add the first case is negative 1 part 1, 1 part 2, and also the second case, 2 part 2 here. But of course we can't change the value, so we have to minus immediately. Avoid any value change. If we just look at the first 3 terms here, it will become start from k equal to 1 until k equal to 3, 3, 3. At the back, we still have plus 1 and then minus 4 here. We double check whether it's exactly the same expression. Now it's exactly the same when n equal to 3, 3, 3. So we are going to use the result. So we have 5, 5, 6, 1, 4.